Prove by contradiction that there are no positive integers p and q such that this is true. This is actually known as a Diophantine equation because there are two unknowns, only one equation, but we're looking for integer solutions, or in this case, positive integer solutions. I'm going to talk about two different ways to do it. Both are going to assume that there are solutions. Assume there is at least one solution for p and q positive integers. A nice way of writing this to say it belongs to the set of natural numbers or counting numbers. That's 1, 2, 3, 4 onwards. And we're going to seek to find a contradiction, so something that we know is not true. Yeah, there's a really neat, quick way of doing this question, but if you've never seen it before, it can be quite confusing because it's like a slightly different way to solve a quadratic. I'm going to do that second, actually. The slightly longer way, but maybe easier to understand, I'm going to go through first. So method one. Right, I'm actually going to make q squared the subject of this. Q squared is going to become 4p squared minus 25. Now this is an even number. Remember, I know that p and q are natural numbers. That's actually going to be at the heart of this. And 25 is an odd number, so q squared must itself be odd. So it's going to be an odd square number. Because I'm doing an even minus an odd, I don't need to prove that that will be odd. I can state it without proof. And then that means I should actually add that, therefore, q is going to be odd. Okay, there's no way that, remember, it's a whole number. There's no way it could be even because an even times an even is an even, an odd times an odd is an odd. So now I'm going to let q be a general odd number, 2n plus 1, where n is also a natural number. And that means that 2n plus 1 squared is 4p squared minus 25. And I'm going to try and make p squared the subject and essentially show that it cannot possibly be a whole number as well. So multiply the bracket out, 4n squared plus 4n plus 1 is equal to 4p squared minus 25. That means that 4p squared is going to equal 4n squared plus 4n plus 26. And I'm going to divide through by 4 now, so p squared will equal n squared plus 2n plus, well, if I divide by 2 once, I get 13, divide by 2 again, I'm going to get 6.5. And p squared is not a whole number, okay, because I've got whole numbers added together, and then I'm adding a decimal to it. Therefore, p is also not a whole number. We could even use the notation, p does not belong to the set of natural numbers, but this is a contradiction because we said at the start it was. We said there is a solution, and now we've shown if there is a solution, it can't be because it's not a whole number. So that means, just to conclude, there is no solution to the equation. To be honest, you can't avoid it being at least, this sort of technical. There's no like really quick, obvious way of doing it. The method I'm going to show you in a second is still like quite very subtle and technical. So just to say again, method one, I've made one of them the subject. You could go with p squared instead, but it seemed to make sense to make q squared the subject. I've then noticed that it must be odd, written it as a general odd number, made p squared the subject in terms of this, but found out that this cannot be a whole number. And that means, although we've assumed that q is, that means that p can't be. This is a contradiction. There is no solution. Okay, it's awkward for sure. Second way, you might prefer this. We'll see. Second way is to spot that this is a difference of two squares. So we can actually factorize it. And normally when you factorize quadratics, you set them equal to 0 first, and you need to if they're sort of general kind of numbers, and then you can find the answers. But now we've got two unknowns. Actually, the way to do it is to factorize it with a whole number on the right, and you'll see why in a minute. Because these are not whole numbers, and there's lots of possibilities that could multiply to give 25. You could have this equal to 20, I don't know, like 12, and this is 25 over 12. Like there's an infinite number of possible solutions, and actually there are an infinite number of possible solutions to this equation. But because p and q are whole numbers, then I've got a whole number times a whole number equals a whole number. It must be the factors of, like, these must be the factors of 25. So we either have that 2p plus q, and this is why this is like a little bit different. 2p plus q is clearly the bigger one. So either that is 25, which means 2p minus q is 1, or we could in theory have them to be the same actually. That's the only possibilities, because 25 has 1 and 25 as factors, or 5. Now if I add these two equations together, I'll get 4p equals 26, but then I'll get that p is 6.5, and this is, this is not valid, reject, because remember p has to be a whole number. And if I do it over here, then I'll get 4p equals 10, but then p will be 2.5, and so I'll reject it as well. And that is enough to say that this is a contradiction. Contradiction. I should probably actually not reject it, because I have found solutions, but now they just contradict the fact that p is a whole number. Contradiction, since p does not belong to the set of natural numbers. And then we can say, let's make the same conclusion. Okay, well done. To find out which one you're happy with, practice both would be my advice. Which one are you going with? It works out nicely here because it's a difference of two squares. A more general case, and it might be that method one is actually the way to go. So it's kind of dependent on the question, to be honest. But there we go. Very well done on your efforts here.